Hi, this time we'll introduce the idea of noise margin and voltage range, you see, which is the range of values in a given digital system that is understood as a 1, and which is the range that is shown as a 0. So that's the idea now. The voltage ranges associated to a given, technology, a given gate technology, and the power supply to which the gate and the digital circuit is connected. So let's talk about this, and then let's emphasize the meaning of the noise margin high and the noise margin low that make possible to connect gates together, and build digital circuits using the same technology. So let's just start now this recording on another concept which is quite important and is maybe the continuation of we had here previously on the idea of a switch or a push button and the gate. So you see, this is the circuit where you are generating a clear 1 and a clear 0, but indeed what you are generating here is a clear 5 balls or VCC balls and a clear 0. You see, if this is 5 balls, you are generating here the VI, which is plus 5 now, or 0 balls. That is the point. When you switch on, you have 0 balls, and when you switch off the switch, you have 5 balls because there is no electrical contact to the ground. And then the level of the current, as I said before, in some way depends on what goes next. A gate, for example. So let's make that connection. Let's imagine a connection to a NOT. And then, let's imagine the connection to another NOT, because you see, a series of 2 gates, that's the most typical circuit ever. Well, one gate or just another one of another kind. You may start inventing circuits from this input, you see. You may consider this to be the input of the digital circuit that you have here. Okay, that goes connected to many other nodes. So, well, right, basically, you may imagine such a thing. A wire and the input, that make it simple like this. Let's connect it to a push button or a switch, and then the output from this first gate that it's connected to GND and VCC and is consuming some static power. Every single gate, you have to remember that every single gate has its power consumption, absolutely. So necessarily a circuit like this, which is based on transistors, bipolar transistor or CMOS technology, drains some current from the power supply, so, or from the batteries or recharger of batteries, as you like. So in the end, that's the typical circuit. Okay, so what I like to show you now? Well, the rails, okay, the rails, you may very well imagine that this is the top rail. This is what we call VCC rail, like in the rail on the train, and down there you have the other rail. That's the ground potential rail. So that's the minimum voltage possible. So you can say that if you are connecting this to a VCC of plus 5 volts, so this is plus 5 volts and this is 0 volts, the reference voltage. This is the negative where you are connecting the black wire, of a voltmeter. So imagine this situation, okay? And now what? Well, this is VI of the gate number 1. So let's label that gate as 1 and that gate as the 2. So what is this? This is in some way VI1, because it's attacking, is driving the gate, the input of the gate 1. And then so you have here a node that you may call B01. But there is a wire, so here you have plus BI2, and so up there you have the plus B02. You see the second voltage of the second, the voltage, the output voltage of the second gate. Okay, so now if you think about voltages in this way, imagine a vertical axis or line like this. You may say that here, yes, it's like that. 5 volts when you are not clicking and 0 volts when you are clicking. That is clear because there is nothing else. Imagine as well that this gate, you know, has an equivalent circuit that has an input impedance which is extremely high. So don't worry about the current that may go up inside the gate, or maybe sourcing from this input is 0. So let's imagine that this is a wire as if it were in the air. Make it simple, okay? That is not true, but you can think about this, especially imagining the value of the R, okay? I mean, look at this. You have the battery, okay? And then you have the resistor R, that is that one. And then imagine that you are generating an electrical contact. And then here is the Thevenin equivalent, you know, of the input of the gate, because this is an electrical circuit. We will talk later about this later on, but now you may imagine that yes, is an impedance. It may be capacitive and with some part of inductance as well, and some ohms of losses. So that is the Z in. So in some way or another, you may imagine that Z in is a huge value compared to R. So all the current goes through the circuit and very few current goes through the Z in. So it is like if it were superfluous in some way, to make it simpler. So I mean that we will talk now about voltages, general ideas about voltages, not about power consumption or other kind of situations. So now if you imagine a vertical line, that is perfect, okay? Then what? Then here you have the output B01. So you see, this may be for you the BI1, and here you may imagine another time this vertical axis, and here you may imagine B01. And now what? Well, this is the output of a real gate, and if you consider the same example as in the previous video, this gate may be the 74, to make it simple and classic, 74 LS-04. This is a hextuple knot. So the couple of gates may be from the same real chip, 74 LS-04. But you know, this is already a digital technology, and it is all the chips of the same kind, LS, low power Schottky, are, you know, of the same logic family. So this gate has to be of the same family and everything the same way. So this is what this is called, the logic family, and the logic family is associated to a given set of characteristics. And that characteristics, these characteristics are going to look like this, you see. V01 means that when high, you see, when high, for example, let it, for example, now you are not, the switch is in this position, so you have here a 1, very well. So a 1 is a 0 now here. But what means this 0? Okay, what is this 0 meaning? Yes, in voltage, B01 means just a range of voltages, like this, you see? A range of voltages. This is what the datasheet of this technology says. And what is this exactly? So it is a range that goes naturally from 0, which is the lower range possible, 0, the power supply itself, and then here you have 0.5 volts. Okay, that is what you have. A maximum, you may call that now very well. Let me annotate it. It is the V, okay, O, the voltage at the output at the low level, you are generating a 0, maximum value. So normally the typical value is going to be in between this, but the manufacturer admits, or the convention, or the people who decided to organize this technology said that you may expect a maximum value of 0.5 for certain gates, for example. So that's the point. Well, so when you talk about the zero at the output, what you get is this margin, right? Look at this. You have a margin of values that are all interpreted as a zero logic. So the same when you are clicking the button, okay? So if you click the button, happens something similar. If you click the button now, or you switch on the button, the switch, you see, you have a perfect connection. So what you are generating here is a perfect zero logic. And so, because it's a NOT, you are generating now a perfect one. What is a perfect one here in a real chip? It's not 5 volts. It is something like a voltage margin, the same as before. But this time, a margin that goes from 5 volts, you see, you have 5 volts up there, and then there is a range of voltages that go down, for example, up to this point. It's not on a scale. I have this not in tension now, but I could do that very well, but it's not important. You have now a voltage range, and all this voltage range is understood to be a logic one, the true, you call true that voltage range. And the data sheet of this technology, because every technology is different, you see, for example, this is one technology. If you pick up another one, for example, I don't know, it is the series CMOS equivalent circuit, like this is the CMOS 4069 UB. There's more lettering here, but doesn't matter. The reference is the 69. 4069 is the same thing. A sextuple not. But it's another technology, so I mean that here that you have different values. But if we keep to this one, all the explanation to this one, we have from 5 down to, let's say it is in the data sheet, I remember, is 2.7 volts. 2.7 volts. So down there to 2.7. So, and in between, nothing. In between, if the digital circuit works fine, you will never have to expect that from the output of the gate you get nothing. You will never get such voltage like 1.5. If you get that, is because the gate is broken or something. So in operating conditions, normal operating conditions, you will expect here a 1 or a 0, and this is the range of voltages that is a 1, and this is the one which is a 0. So very well, okay. And now you can label that, you see, VO high minimum possible, because the maximum possible stays attached to the VCC, the rail, the top rail. So you see, so that's for a single gate. Now what happens here? You connect other gates just to generate a circuit, and normally you will have not 2 gates but many more, absolutely. So look at what happens here now. You see, you can organize another axis now, but well, you may suppose that this is VI2, or you know, the characteristics, the input characteristics associated to the VI2, which are the same as the VI1 because they belong to the same family. But you see, here at the input of this gate, the gate number 1, it is clear that you are driving this very well with a 5 when 1 and 0 when 0, because the voltages are generated from a real chip, from a real switch like this. But now look at this, where the input voltages of this second gate are going to come from. Well, this is very clear. It is the output from the first gate. So what is the meaning of this? That it has to be compatible. The circuits has to be of the same logic family, because they have to have compatibility. You cannot power this chip at 1.2 volts and the next to 24. That has no meaning. There's not going to be understanding here. So this compatibility, it is clear when you represent this second axis. You see, this is the axis or the line respecting the voltage output is. And this is the axis representing the input. So what you have to say here? Look at this. Even if you are generating a 1, like now, you are generating contact, a 0, this is a 1 here. So even if you are generating a 1, which is the minimum voltage possible, okay, this gate at the input has to understand that as well as a 1, because if not, there is a problem. Imagine that this voltage, which is very possible because it's in the data sheet as classified as the minimum voltage high, goes as an input to a value that do not correspond to a 1. You see, has no meaning. So in reality, you have to take this like that. So all these large, you see, voltage margin has to be what is called now a 1. But from the input perspective, you see, and it has to cover the VOHigh minimum from the outputs of gates of the same kind. I mean that these can be leveled this way. So this is going to be VI what? VI, because it's an input, you see, VI high minimum, the same, you see. And if you see, if you keep an eye on the data sheet, you will observe that this value, it is 2 volts for this logic family LS, right? 2 volts. And the same when you have the switch off, generating a 1. If you generate a 1, this is, you see the point, this is the perfect one because it's clear 0, but now the 0 has become, you have the switch off, you have a 5, at the input, this 1 in blue, now you've got this 0 in blue, the 0 becomes something like this, and now imagine that you are driving this gate number 2 with this voltage, which is possible, as I said before. So now, you know, the situation is very clear, the same. You have to cover it like this. The level, the maximum possible level that is understood at the 0, generated by the gate number 1, has to be understood correctly as a 0 as well. So that's the situation. That's the real, that is what works. Nothing that is not this is not going to work. You see, this is what makes the gates compatible. And, you know, if you go to the datasheet, you will see that this is 0 volts, this is 5 volts naturally, this is 2 volts, you see, and this is 0.8 volts. And this has also a name. If you go to the datasheet electrical characteristics, you will see that what? This is VI low maximum. You see? The voltage input at the gate at the low level maximum possible. So logically it would be better if it was 0. 0 is okay, but even if it goes up to 0.8, it is compatible, it is understood. So you see, so what is the meaning of this? And then, well, the output V02, we are now going to leave it in the air, but in the next exercise we will connect here some LEDs, okay, some light emitting diodes. So that is going to be another explanation, how to drive a light emitting diode connected to the output of the digital circuit, how to do that, knowing all this information, because you know, if you have to drive a LED, you need current, and this information is going to be essential or necessary. So now let's finish with this. You have the axis that you see the situation now. I guess that you have understood that very well. So what goes next now is to imagine the forbidden zones. You see, like this. This zone here is forbidden. You better never uses it for nothing. This is a forbidden. You see, has no meaning. Working with this margin of voltages, a margin of voltages that is not a 0 or a clear a 0 or a 1 has no meaning. So here is the same thing. This zone, you see, has no meaning. It's completely, it is for avoiding it. You better don't use it, because you will never know what is going to happen at the output of the circuit if you are attacking the input of a gate like this with a voltage, for example, of 1.5. Who knows what is going to happen? So you see, the other thing related to this is that the tolerance to the noise, because you know this is a wire, right? And this wire can get attacked, you know, in some way or another. This wire can be attacked by a noise, you see, an electrical lighting stroke, or a motor, you know, switching and generating sparks, and you know, switching on and off, power load. That is what these kind of devices do, generate noise. So the wire, for example, may be clearly generating a 1. So, for example, the typical value, let's imagine that the typical value is 3.5 volts. So the gate is generating a 3.5 volts, and then what? Is attacked, or it is picking some noise. So what is the meaning of this? Well, if the noise is not that high, it happens nothing here, because even if the voltage is variable around the 3.5, you see, is covered in the margin that is understood as a 1. The problem is when it goes larger than this and it's going down, you see, or if you are driving, for example, let's imagine the typical value here, 3.5 volts, a typical value of this kind of 3.5, 0.25, for example, 0.25, and now you have here noise that is picking from spark or something. So look at this. Now you have, if you have a variation here, but this variation do not reaches this point, is okay, it is not detected. But look at this, it is something else. There is this possibility, you see, I need another color to do that rightly. So yeah, this is, let me use this one, the orange. This is the one that I'm talking about. This is the level, VOL maximum, and this is the other level, you see? So this is what is called the voltage, the noise margin low, you see? The noise margin low. And here you have the same concept. So this is the VO high minimum, the minimum voltage that is possible, and this is what the input of the same kind understands as a 1. So you see, you have this security margin indeed. This is the noise margin low. And what is the meaning of this? So, well, what was exactly what I was explaining here. If you have that this situation that if the value that is supplying the gate is attached to a noise, and now the instantaneous value of this voltage for some microseconds go down, you see, that even this is a problem, you see. So if this 2 volts is crossed, what happens? Well, you have an instantaneous value that is below of what is understood, you see, for this time. Perhaps this is only a few microseconds, but you know, a microsecond for a digital circuit is a huge amount of time. It works in the range of nanoseconds, and we will see. So a microsecond, even it's that short, and that, you know, spike that short, doesn't matter. It is huge amount of time for a digital circuit of today's technologies. Perhaps not like that, but the FPGA technologies of today works with a very, very teeny in-time signal. So that is a very long time, 1,000 nanoseconds. So, well, for all this time, while the signal is below the VH high minimum, you have a problem, because you know the real voltage that you are applying to this gate is under, I insist on this, is under what is understood as a 1. So it is clearly in the forbidden zone, so you will never know what is going to be the output. So now imagine that here you have processing circuits. What is what you are going to process? There is no way to know it, because here no one knows what kind of logic. So the circuit may go wrong. It's maybe possibly for this short period of time the circuit will do not understand what kind of level is at the input, and in this way perhaps the circuit cannot process digital signals. So you see, you have this noise margin security for this kind of situations, and you can calculate that because you have the values from the data sheet. You see the noise margin high is, the VO high minimum minus the VI high minimum, right? And the same for the noise margin low at the low level. It's the same idea. You have a signal, it can go like this. You see, you can have a spike in time that goes for some time above what is understood as a VAL maximum. So this is the same concept here to write. So this is the VI low maximum, right? Minus that one, V0 low maximum, the same. So that's the formula, or that's the definition, and if it has to work, you have to guarantee that all the time this difference becomes positive, you see, strictly positive, because if it's zero you have a problem, if it's negative you have more problems. So in that case for TTL, you see, from Schottky low power TTL, a very old technology today, but for the sake of understanding, this is okay. You can do the same calculations later by your own, changing to a CMOS technology or the same chip, 74, HCT. That is an advanced one. The same chip, you see, but with this different technology. That one you will see that has that kind of features improved a lot, It has symmetrical high and low margins and the like. You see here, there is a lot of difference between what is understood as a 1 and what is understood as a 0, and that is really a problem in modern circuits. So kind of advanced technologies today has solved that situation, making the ranges more symmetrical and faster circuits, and generating better noise voltage margins. So in this case, as I say, let me go finishing this. If we talk about LS, and this is 2.7 volts minus 2 volts, so this is a voltage margin of 0 plus 0.07 volts, so that's okay. So this is the noise, the electrical noise that you can tolerate at the level high when generating a 1, and when generating a 0 is lower than that. So it is VI low maximum. This is 0.8 volts minus 0.5 volts, because this is what this gate can generate as well as a 0. So this is only plus 0.3 volts. So you see, this is what we call noise margins, and it's quite interesting feature. The idea that there is a tolerance here. A very large tolerance first with respect of what is understood as a 1. Okay? And a 0. And then there is a tolerance towards, absorbing noise in some way. You can talk about that. Okay, so this is the features that you can deduce reading the data sheet. And so that is the typical circuit attached to a real push button. Later we will improve that again, because there is going to be the idea of debouncing the signal, because I can advance you that the signal is not going to be that clear. You see, if you imagine now that in time, this is, for example, V02, which is the same as V1, you may say that this is like that. Okay, this is the switch, You see, like now, the switch off, you have a 1, you have a 0, and so again you have a 1. So, okay, so the switch off. 1, because in time, up to this point, from 0 up to this point, TA, the switch is off, and you have a 1. And then you do this operation. You at T equal to TA, you switch on the device. So now the switch here, the switch is on. And that means that you are generating a 0, the red one, here a 1, and then a 0 again, like that. And the output of the B02, okay? Let me finish with this because it's interesting. B02, 0. So that's the point, you have a 0 in time. Switching the button, you have this, you see, this perfect signal. 0 time switching from 1 to 0, so that's the ideal signal. And that is not possible, right? So later we will learn how to invent digital filters to get that kind of signal, that kind of ideal signal from the real one. Because the real one is not that good, you see? This is the ideal situation, and the real one is something like this. V02 in time, okay? You may imagine that the same time equals 0, and the same time equal TA. That's not a problem. But what I like to say here is that the real signal is, you know, it's like this, and then you are ordering the switching action. You switch, you see, T equal TA, you switch the button, and what happens here? This. You have electrical noise, and in the end you have the signal stabilized. So yes, this happens in some milliseconds. That's the real thing. You can see that in an oscilloscope. So in the end, you have what you want, which is a 0. But you know the 0 is still that way. So that's the 0. Nothing happens because it's in the range, you know. This is very well, this is in the range, is, you see, it's quite large. So it's not a problem if this is in the range of some milliseconds, and this is the same idea. This is clearly a 1 and this is clearly a 0. But in between, when you have this switching action of a push button or a key in a computer, you generate that kind of signal. Well, this is an exaggeration, but it's not. And besides, that depends on the pressure of your finger, depends on the person, depends on the technology. So there are many factors, but indeed this is what you've got. So we will solve that in P6 with a digital circuit that we will make it work as a digital filter. So we will, from a circuit, from a real signal like this, we will try to obtain such a thing. A perfect digital signal like this. Click, click, click. Something like that. But that's a matter of the chapter 2, when we have time to study later